Hi, this is Mr. Manley. In this video, I'm going to look at analyzing higher degree polynomials. And there's not much new conceptually here. It's really applying concepts that we already have. There's some nuance and definitely a little bit of newness to it. And there's some aspects of polynomials that perhaps you've been introduced to, but maybe you didn't fully engage with them or fully incorporate them into your thinking about polynomials. So let's try and do that here. I'm actually going to take this one and this polynomial that I'm looking at right here and just say, what does that look like to you? And if you understood the discussion of polynomials in an introductory lesson on polynomials, you would say, that looks like it's probably x to the fourth. But you would also know that it could be x to the sixth or x to the eighth. Because any degree polynomial, it has a maximum number of changes in direction, and it could have less. So x to the eighth could look like this: 1, 2, 3, 4, 5, 6, 7. It's always the maximum number of changes in direction is always one less than the exponent. So this could be x to the eighth, but that's the maximum number of changes in the direction. It could have less. It could go 1, 2, 3, 4, 5, and that could be x to the eighth. So this little 1, 2, 3 changes in direction, that could be x to the eighth. Now it can't be any odd, and hopefully you've picked this up, that odd polynomials always have opposite directions on their end behavior. Even polynomials always have the same direction on their end behavior. So that's something that I hope you inferred, or that you might have inferred in a previous introductory lesson. So what could this be? If I look down here, I skipped ahead to question D. Which of the following is a possible degree? So it could be fourth degree, and it could be sixth degree, and it could be eighth degree. If there's a 10 there, it could be 10th degree, 12, 14, and on. Okay? All right, let's look at some other questions here. Over which intervals is the function decreasing? Okay, so decreasing is, we can talk about decreasing and we can talk about increasing, and that is reading, so to speak, left to right, where up is an increase and down is a decrease. That should be pretty intuitive. So over which intervals is the function decreasing? Well, it's decreasing is down. So that's going down here, and it's going down here. And what are those intervals? Those intervals are, looks like this one is starting at -1, and it goes down until it gets to, looks like +3. Right? Those look like XY coordinates, but they're not. Those are intervals, right? This is interval notation that is telling us values of x on which this function is decreasing. This guy here, this one on the right, it starts at 7, and it keeps decreasing for values of x that go to infinity. Don't talk about that it's decreasing down to -infinity. We're talking about the x values here. For what values of x is it decreasing? So let's see, that would be here, and 7 to infinity would be over here. Okay, so that's another one. Let's go to the next question. At which x values does the function have a local minimum? Okay, I think this is a problem that anybody in pre-calculus up to this point would know this answer to. There's a local minimum there, at which value of x is going to be 3. That's it. If there's more than one, there can be more than one, right? There can be more than one local minimum, but in this case, there's only one. So that was 3. All right, what is the sign of the function's leading coefficient? Okay, this is a big one that is calling back to the introduction to polynomials. I hope that people know this. It's a major point of the introduction. This is opening down, so it is negative. Let's just consider a cubic, like a cubic that could look like this, which could also be 5th or 7th degree. And that's going to be positive leading coefficient. And this one is going to be negative leading coefficient. Just a review. Okay? Let's take a look at another series of questions. And we do need to introduce a big new concept here on this. So let's see what we can answer without the big new concept. Choose the end behavior of the graph. All right, we've seen problems like this before. X, 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 though there are 2 x's there. 2, 3, 4. So this is x to the 4th. It's an x to the 4th polynomial, and there it's negative. So what does that mean about the general idea of it? This is the general idea. So it's falling on the left, falling on the right. And that choice would be given in this drop-down menu here, but I'll just write it. Falls left, falls right. Okay? All right, list each real zero of f according to the behavior of the graph at the x-axis near that 0. If there's more than one, separate by commas. All right, so this is a big idea here that I need to introduce. And that is when I have a repeated 0 that is even, all right? So this could be squared, or it could be to the 4th power, or to the 6th power. The 0 that I get from that, and do we understand, let's just talk about the zeros first. So we understand the zeros of this, right? What are the zeros of this function? Can you tell that? I have a 0 at -1, right? X plus 1 gives me a 0 of -1. I have a 0 at 2. This is synonymous with x-intercept, right? And I have a 0 from the x. What 0 do I get from the x? 0. Why are these called zeros? Because if I plug this value in, this whole thing comes out to 0. If I plug a 0 in here, it doesn't matter what happens here and here. 0 times that is going to be 0. That's why they're called zeros. And then they're also x-intercepts, it so happens. So these are the zeros. Now, when a 0 has an even power, it's an x-intercept that does not cross the x-axis. So that's kind of a big idea, right? That maybe you didn't know, but if you think about it, maybe you did, because you know about parabolas, right? Like if I just had x squared, and that has a 0 at 0, and that 0, it doesn't cross the x-axis, it just hits the origin and bounces off. So let's take a look at, before I answer the questions down here, let's just take a look at interpreting. I want to interpret this and show you what we can do with all this information. So I've got a 0 at -1. I've got a 0 at 0. I've got a 0 at 2. This is x to the 4th. X to the 4th. falls left, falls right. So I just go out to the left and go falls left, falls right. And then I've got this big idea that I don't cross the x-axis at -1. But there is an intercept there. So look, there. So I've got my intercept. There, but I'm not crossing over to the other side. All right, and then the other intercepts do cross. So I got to get back up, cross, and then come back down and cross. So look at that. I mean, I have a pretty good graph of a quartic function there. There's more information that we could find, and that's one of the topics of calculus, is finding the rest of this information. But that's a good start. All right, so now let's go and answer these questions down here. So the zeros where the graph crosses the x-axis. Can you answer that question? What are the zeros where the graph crosses the x-axis? It crosses at 0 and 2. The zeros where the graph touches but does not cross. Where is that happening? -1. All right, find the y-intercept. Easy, right? We just plug in a 0 for x. So if I go 0, 0, 0, what does that come out to? That comes out to 0. So we got the y-intercept 0. And then it says graph this. All right, now if you're working on ALEKS, then you're going to have to learn what the interface or see how the syntax of the graphing works within ALEKS. If we're not on ALEKS, or if we're on a pencil and paper, then you could really just do what I did up here. That's a fine graph of this quartic function. Okay, so that's quite a bit to digest on polynomials, just with that one big new concept, right? But if you get that one big new concept about not crossing zeros, not crossing the x-axis, and you can incorporate that with all the other things that you know about polynomials, then you have it. That's all there is to it.